We already seen that classification is an important category of problems in machine learning. And interestingly, classification is also the most rigorously studied set of algorithms in the context of machine learning for its availability of labeled data, that too categorical. So in view of that, there is a plethora of techniques that have been presented in the literature for classification. So roughly, if you see classification, it's basically when you have a whole bunch of input data and you have output data which is basically a labeled data. It can be binary, it can be multiple classes. But the idea is you have a whole bunch of labeled data where input is correspondingly mapped to a particular class. So here we're talking about a classification as a set of techniques which take a set of labeled data, create a classifier, which when given a new input is able to give us most probable output class. So given this, we also know that the way to evaluate a classification function or a classifier is by separating the original labeled data into a control set called test set and a training set on which you derive a model, and you use it to derive different metrics like accuracy, sensitivity, specificity, F-score, recall, or precision. Then we also saw how we have techniques like area under the curve of an ROC curve make sense for understanding how good a classifier is. Now just to look at a summary of the different techniques that are being proposed in the context of classification. We first look at a very basic technique which is basically called as logistic regression. Is technique number one for classification, where you kind of look at a model in terms of an equation like y equal to 1 by 1 plus e to the power of minus m1 x1 plus m2 x2 plus so on plus c. The idea is we use something like a sigmoid function applied to a linear equation, and we try to derive a curve of the form something like between 0 and 1, a curve which goes like this, so that majority of the classes, majority of the data either falls here, or you can approximate it to either 1 or 0. And then what happens is this becomes a way of transforming something which is seemingly a continuous equation into a discrete class choice. So logistic regression is one of the first classification technique which is used in the context of machine learning for basically classifying a set of input data into one of the classes. Logistic regression is useful because it is simple to use, it is reasonably accurate in majority of the cases, and it yields reasonable results with reasonable accuracy for a major set of input class of problems. Going beyond logistic regression, we look at another category of classifier, namely we call it as decision tree. More specifically, we call it as classification tree, where the idea is the classifier is output in terms of a variable and at one point you take one variable, find out a certain dividing point for the data and divide two branches. So ultimately then you may decide to take another branch here. Here again you may take a different variable. But the point is, at each point you divide the search space into two parts. Second, you decide upon a suitable variable value combination to split the search space, and this is decided based upon different factors like entropy or Gini coefficient, depending upon the metric you choose, which we'll study in detail when we look at decision tree. But the basic idea is ultimately every leaf node should be a class of the classifier. Let's say we're talking about a binary classifier like true or false. The leaf node should be one of the classes of the classifier. So ultimately in classification tree, we look at creating a decision tree with at each point a branching being done, and at each point a particular variable value combination is chosen as the segregating point which branches off the search space to two parts or even multiple parts. And the beauty of this kind of a knowledge representation is it can also represent a collection of rules. For example, you can say here, go by the path from the root to the leaf node. You will convert that into a rule. For example, here we say x1 is greater than equal to 2, which is this branch, and x3 is greater than equal to 4 implies false. So this is one rule we generated by passing on this path. Similarly, go around this path, you get one more rule. You get this path, you get one more rule. You get this path, you get one more rule. So effectively, a decision tree can be used as a representation of a succinct form of a collection of distinct set of rules. So that's why decision tree is one of the most powerful classification technique because of multiple reasons. One, it's visually representable. Second, it can be viewed as a set of rules. Third, we can comprehend what the model is about. Fourth, we can actually use this as a knowledge representation mechanism for the original data instead of the original piece of data by approximating it with the collection of rules present in the system. So all of these are very appealing. But only issue sometimes with classification tree is they suffer from the problem of overfitting the original data. Going beyond classification tree, yet another important category of techniques involved in classification use something known as a technique called name base. Right? So name base is basically uses the base theorem as the basis and produces a classifier based on the principle of applying name base theorem on the original data and produces a classifier based on which you can separate it to separate classes. What is base theorem? Base theorem is basically a way by which if you know the prior probabilities of some event, all of them suppose are mutually exclusive, two events P, A1, A2, and you know some consequent event which is dependent upon the probability, say B, and you typically know that if A1 has occurred, what is the probability of B occurring? Or if you know probability of B, A2 occurring, then we typically will look at computing the actual probability of one of the choices given that you have observed a B by use of Bayes' theorem. And how is that used is basically it says that if you know probability of A1 which is a prior probability and you know probability of B given A1, then so what we have found out is, if you know the fact that an event B has occurred because of A1 or A2, now we want to know what is the likelihood that it is caused because of A1. Then Bayes' theorem allows you to approximate the conditional probability of B having occurred or the probability of A1 by saying that P of A1 times PB given A1 divided by PA1 times PB given A1 plus PA2 times PB given A2. So this is a way of approximating the probability of the class being A1 or A2 given observed motion of A. So this is a powerful way of deriving a classifier for especially classification algorithms.